Would you believe that this classic Aneroid Barometer is actually a powerful ESP32 S3 microcontroller? Today I will show you how, using LVGL library and Squareline Studio, I created a device that 100% imitates the mechanics of the past, but with digital precision. From connecting the BME280 sensor to calibrating the altitude, step by step we will build a functional weather station in a beautiful retro package. This project is sponsored by PCBWay. From concept to production, PCBWay provides cutting-edge electronic design solutions for global innovators, including hardware design, software development, mechanical design, product testing, and certification. PCBWay engineering team consists of experienced engineers in electronics, embedded systems, and product development. They successfully delivered hundreds of projects across industries such as medical devices, industrial automation, consumer electronics, smart home, and IoT. Also, don't forget to participate in the 8th project design contest until January 31st, where you can compete in 3 categories: electronic project, mechanical project, or AI/OT project. PCBWay has all the services you need to create your project at the best price. Hello, a barometer is a scientific instrument used to measure atmospheric pressure. Rising pressure generally indicates improving weather, and falling pressure usually indicates approaching wind and rain. Steady pressure indicates stable weather conditions. In this project, I will describe a very simple way to make an Aneroid barometer emulator. In fact, modern digital electronics are used, with the help of which the functionality of a classic mechanical barometer is 100% imitated. Aneroid barometer contains 2 arrows, a black measuring arrow and a yellow reference arrow. The way to predict the weather is as follows. We need to match the black measuring arrow with the yellow arrow. After a few hours, if the black measuring arrow has moved to the left of the yellow one, unstable weather will follow, while if it moves to the right, improvement and stabilization of the weather will follow. If the 2 arrows remained matched, no change in the weather condition is expected. In the original instrument, the reference arrow is moved with a button in the middle of the instrument, and in this case this function is performed by rotary encoder. This device is extremely simple thanks to the CrowPanel Round display, which contains a built-in ESP32 S3 microcontroller and also rotary encoder. So it is only necessary to connect BME280 module to the corresponding I2C port of this display module. This is my first project using the LVGL library and Squareline Studio, which allows you to create incredible visually effective and functional projects in a relatively simple way. This time I will not dwell on the method of developing and creating the code and user interface in Squareline Studio, because it has been described in detail in many previous tutorials, but I will briefly describe the procedure to successfully recreate this project. The following is a detailed description of the installation of the device using the given libraries. First you need to install Arduino IDE version 1.8.15 or later. Then you need to install ESP32 core version 2.0.14 or 2.0.15 according to the instructions on the LCrow GitHub page. Now in Tools, Boards, ESP32 Arduino, we need to choose ESP32 S3 dev module. In this board we need to make several changes to the properties. We need to set flash size to 16 MB, PSRAM enabled to QOP PSRAM, and partition sham to huge APP. Next we need to install LVGL library, specifically version 8.3.11. So this is LVGL library. You also need to install the Arduino GFX library as well as the Adafruit BME283 library for sensor module. All these libraries and necessary files are given at the end of the text. Next comes another important operation, namely in the root of the libraries folder. Most often this folder is located in the user documents Arduino. You need to copy the configuration file for the LVGL library named lv.conf.h. Now we are done with the support and need to compile and upload the given code. For this purpose we unpack the contents of the CrowPanel.zip file without changing the name of the internal folder. We enter in the folder and start the ino file. In this way the code is opened together with the necessary user interface files that were previously created with Squareline Studio. Now we can compile and upload the code without errors. As for the code, it is made in a way that we can simply change several parameters for normal and precise functioning of the barometer. The altitude at which we are is entered in this line, in my case 700 meters. Next, the frequency of reading the value from the sensor is defined in this line. Next, calibration of the barometer is performed in this line, and here we put a value for the angle so that the arrow shows the exact pressure value that is displayed on the serial monitor. And at the end, the resolution with which the yellow arrow moves, i.e. the change step, is set in this line in void loop. Now let's see how the device works in real conditions. Immediately after turning on the device, a detailed image of retro Aneroid Barometer appears on the display, with the black arrow briefly stabilizing at the current relative atmospheric pressure. Generally, if the pressure is above 113 hectopascals, it indicates stable weather conditions, and if it is below 130 hectopascals, it indicates unstable weather. For us, the data on the change in atmospheric pressure over a certain period of time, at least 3 hours, is important. For this purpose, we set the reference yellow arrow exactly above the black one. Now, if after a certain time the black arrow has moved to the left in relation to the yellow one, the weather will become unstable, and vice versa. If it moves to the right, the weather will stabilize. If the two arrows remain overlapped, like in this case, there will be no change in the weather. By pressing with a finger above the sensor, first increasing pressure, we see how the arrow slowly moves to the right and then returns to its initial state in a short time. It can be seen that this barometer completely emulates the mechanical Aneroid barometer. The only difference is that with the mechanical barometer, in order to read the current value accurately, you have to tap the glass several times, and in this case it is always accurate, which is certainly a great advantage. Not to mention the precision, which in our case in order of decimals. We can also read the current pressure in a serial monitor. And finally, a short conclusion. This project shows how modern electronics can completely replace and improve the classic mechanical instruments, offering digital precision in a beautiful retro package. With this barometer, you get not only a functional weather forecasting device, but also a visual impressive addition to your home.